Hello, everyone. I'll be sharing our project on Terahertz spectroscopy for fingerprinting applications, which is part of the program on the Terahertz research and innovation leading to commercially viable Terahertz time-domain spectroscopy systems. The program is headed by Dr. Elmer Estacio from the National Institute of Physics, and I'm Alvin Carlo Tapia from UPLD, leading the project. This presentation will tell you about terahertz and the impacts of the missing wave. As we traverse the electromagnetic waves from lower to higher frequencies, there are applications for different frequency bands. We are used to using microwave ovens to heat food via microwave radiation. The signals from remote controls to our televisions use infrared radiation. And the colors of the world that our eyes can see are within the visible light region. Terahertz, the missing wave, is sandwiched between the microwave and the infrared region. The frequencies and dynamics within span from 300 gigahertz to several tens of terahertz. This frequency band can provide essential information regarding the motion of charges in materials and how they interact with the lattice or atoms arranged in the material. This is also highly useful in probing the fingerprint or molecular structure and network, since some molecular vibrations lie in the terahertz region, which are also relevant to collective motion and molecular interactions. Also, terahertz is a non-ionizing millimeter wave where detection is not affected by background temperature. Thus, it can be used for sensing and imaging applications. How will terahertz impact society? Some direct applications include communication, where data can be transferred faster than radio waves and microwaves. For medical imaging, terahertz has high contrast in various tissues without being highly scattered, and is also due to strong absorption of terahertz radiation by water. We can also observe charge dynamical behavior of materials for electronic applications. For screening applications, concealed substances can be identified and imaged at the same time. Terahertz can also offer quality assurance for pharmaceutical companies. Terahertz market has been forecasted to be around $1.4 billion by 2025. This suggests that the Philippine society and industries should ride the terahertz wave to be at the forefront of terahertz technology. For our project, we intend to differentiate substances and image them in concealed packages. This takes advantage of the penetration of the terahertz waves while it interacts with the sample. This then measures the spectral fingerprint of substances. The technology is currently being used at airports abroad. Since it can profile substances, we also intend to collaborate with pharmaceutical industries in profiling various compounds and their bulk morphologies. For a certain chemical compound, various forms can exist with different properties and effectivities when it interacts with a biological system. This differentiation has been profiled by terahertz spectroscopy. Since terahertz waves interact with the bulk system, it can differentiate particle sizes through the arrival of pulses in the detector. This takes advantage of the amplitude and phase measurements of the technique. How are these measured using the technique? First, an ultra-fast short laser is split into two. One is for terahertz emission, and the other is for terahertz detection. The beam is directed to a photoconductive antenna that generates terahertz radiation. It then passes through the sample, and the transmitted terahertz signal is detected by another photoconductive antenna. The samples can be measured with a reference. The terahertz signal through the sample has smaller amplitude and with a shifted phase in the time domain, as seen at the upper right figure. These can measure the terahertz absorption and index of refraction respectively once it is converted to frequency domain. We can also calculate other terahertz optical and electrical properties of the material, like conductivity. In our previous projects, our collaborators from the National Institute of Physics have developed terahertz photoconductive antennas for terahertz instrumentation, such as the figure on the left. On a separate paper, they have developed antennas that show higher terahertz emission by applying magnetic field. These are very relevant in the Philippine context as we developed our own terahertz systems. In parallel, we have also used terahertz radiation to probe the properties of conducting polymer pellets. We found that there's an increase in the conductivity with temperature consistent with phonon-assisted hopping model. This model suggests that as the temperature increases, the barrier between two sides is decreased, leading to an easier transport of charge from one side to another as assisted by lattice vibration or phonons. We also observed localized and percolative conduction for various composites. The advantages of terahertz technique should be realized for the future potential applications of terahertz, such as being a non-destructive method while determining spectral fingerprints and material characteristics, which are relevant for detection and inspection. Our group looks forward in the coming years to the establishment of linkages with industry and terahertz innovation in the country, as we continuously develop novel materials for terahertz antennas and instrumentation systems for very relevant applications in human health and security. For the moment, we hope that the researchers, both in the academe and industry, would explore the future with terahertz waves. Like a Filipino sari-sari store, we are selling terahertz science to our future customers, the Filipino people. Maraming salamat po.